Okay, so what we're gonna do now is we're going to use Excel to solve a problem. We know how to type formulas into this problem, but now if we wanted to have something like, for example, the stock price. And we can just put a price in the box, like $50, like current price of stock is $50. And let's say for some reason this would never happen in the real world, but you know that the stock price doubles every 3 years. There's no stock that would actually do that for sure, but let's say, so we could say something like we have a factor per 3 years. And we're gonna type in 2, and it doubles every 3 years. And then the question becomes, how long has this been going on? So we could say a number of years. And let's say this went on for 2 years. Then we could say, what is the future price? This would end up being a formula, and the formula we want to put in would be whatever the initial price was, so whatever this box is. And let's say this is C3, then we'd say plus, it would be the factor raised to the power of the number of times the factor got hit. So that would end up being something like C4 raised to the, so this little at symbol is raised to the power of, and then we got the next box like C5. And in Excel, it is implied, although it's sometimes safer to do this anyway, we could put parentheses around here to say that this operation should be performed before this one is done. I'm sorry, this should be done. But the exponent operation has higher precedence than multiplying and divide, so this would have been performed anyway. We left the parentheses out, but it's a little bit clearer to put it in anyway. Okay, so if we put in a formula like this, sure.
Shouldn't it be C4 times C5, C4 raised to the power C5 divided by 3? Because you're raising it every 3 years.
Wait, I'm sorry, this should be, so it should not,
Should be C4 to the 1 and C5 equation? Is it your factors every 3 years?
no, it's doubling
Yeah.
every 3 years. Oh, I'm sorry, I see what you mean. I should have called this the number. Let's say this was the number of sets of 3 years. This would end up being 9 years. What would be the best word to put in here? I guess time period. Right? Yeah. Number of periods. But that's a good point. I didn't want that to be confusing. So let's say every 3 years the stock doubles, and then the number of time periods we do this is, we'll just say 3 for now. Number of periods is, and then if we decided we wanted to change this, make this number a 3. We would end up with $400. Okay, I mean, that was a good point to bring up, but, so what we're doing is we're saying if, for example, the stock price doubled by a factor of 2 every 3 years, and then we let this happen for 3 sets of 3 years, which would be 9 years, what would the price be? So it would go from $50, 3 years later it would be $100, 3 years after that it would go to $200, 3 years after that it would go to $400. Now, if we were asked the question, when will it be, that takes a number that's not even a multiple, when will it hit $130? How long will it take till the stock goes from $50 to $130? We can use goal seed. So what we're really saying here is we want to, this box ends up being the answer that was calculated in the formula. Now we've decided we know what the answer is, we need to change the inputs to get to that answer. So we can only change one of the three inputs to get to the answer we want. So we could use a goal seek, which basically, we identify the answer we want, and then we identify one of the boxes, and only one of the boxes, that was used in the formula to calculate it when we let Excel let that run a free value until it finds the answer. So what we can do here is we could say, we could go to this tab that says the what if analysis, and then we pick goal seek, and we set the cell. This will be, we're going to set the cell that has the answer, that would be this cell, and we want it to be, let's say for our question, $130. And now we want to change, we can only change one of our inputs, let Excel let that one vary to get to that answer. So now we can go to this box and say, I'm going to allow this cell to be the one that varies. What we've done here is we've said, we have a formula that calculates an answer. This $400 comes from these three inputs. So right now, these three inputs can be whatever we set them to, and we'll get our answer. Now we're doing the reverse. We're saying we want the answer to be $130. If we allowed multiple inputs to vary, then we would get a collection of answers. We'd say, well, for this factor, you could have this many periods, but if you change the factor, you get a different number of periods. So we'd have a collection of answers. So they only allow us to pick one box to vary, and then they'll vary it for us to get the answer that we're trying to get. So we hit OK with this. And then this thing is basically telling us that the stock price would hit 130 in 1.3785 number of periods. And then in this case, each period is 3 years, so you have to take 1.375 and multiply that by 3, and that'll tell you how many years from now this stock would hit $130. Okay. So we can say we like that answer, or we can say we don't like that answer. If we say okay, then it'll write those values to these cells. Okay. Another interesting problem, and maybe a little bit more complicated of a problem, is a problem that goes like this. And this is what are generally called maximization or minimization problems. And these problems work like this. Okay, so suppose we had a set of ingredients we're trying to make. We're a beer and ale manufacturing company, and we can make beer, and we can make ale. And let's say to make 1 barrel of beer, we use 1 barrel of corn, and we use 2 barrels or bushels of hops to make beer. And then when we make a barrel of beer, we can sell it for $15. If we want to make ale, that takes 3 barrels of corn, 3 bushels of corn, and 3 bushels of, 2 bushels of hops. Well, we can sell that for $20. Now, we only have, so these are our constraints. We only have 6, as our total amount of ingredients to make beer and ale with. And the only thing we know how to make is beer and ale. Okay. So now the question is, what is the smartest way to use our ingredients, assuming our goal is to make as much profit as we can? So the way this problem could be viewed mathematically is by looking at it like a graph. And if we wanted to make, from the point of view of using corn, if we used 6 bushels of corn, we could, and made just beer with it, we have enough corn to make 6 barrels of beer. But unfortunately, we don't have enough hops to do it. But from the point of view of corn, so this is beer, and this is ale. From the point of view of corn, if we dedicated all the corn to beer, we have enough corn to make 6 barrels of beer, assuming we had unlimited hops. And we also have enough corn to make 2 barrels of ale, assuming we had unlimited hops. So there's really like a straight line of how much we dedicate, how much of the corn we dedicate to beer and how much of the corn we dedicate to ale. So this would be a straight line from 6 up here to 2 down here. Then using the same idea for hops, if we dedicated all the hops to making beer, we could make 6 divided by 2 is 3 barrels of ale. And the other extreme was to dedicate, that would be 3 barrels of beer. So we take our 6 bushels of hops, 2 per barrel of beer, we could make up to 3 barrels of beer if we dedicated all the resources to beer. And if we dedicated all the resources to hops, it's the same thing, 6 divided by 2 would also be 3. So, we have a line something like this. Okay, so now, our goal is, we can choose to use as much beer or, as much corn or hops to make as much beer as we want. Any ingredients we don't use, we don't get any credit for, we just lose them. So now, from a mathematical point of view, what are possible answers to this question? Well, we could never say, I want to make 4 barrels of beer, because one of the ingredients we don't have enough of, we don't have enough hops to make 4 barrels of beer. We only have enough hops to possibly make up to 3 barrels. We can't go any higher than that. So we couldn't say like a point, any of the points out here are possible candidates for the best answer because we don't have enough material. We actually, up here, we don't have enough hops. We also couldn't use an answer out here because we have enough, corn. If we pick the number out here, we have enough hops, but we don't have enough corn to come up with that number. So, for example, we couldn't say, let's make 3 barrels of ale because we don't have enough corn to do that. So the only feasible answer, possible candidates as the maximal answer, is anything in this region. We have enough material to make, for example, I'll put a point right here, the 1 point. We have enough material to make 1 barrel of ale and 1 barrel of beer. We have enough material for that. And actually, we'll have left over, it looks like. So that's a possible candidate for the best answer, but maybe somewhere there's a better answer. Maybe 1 barrel of ale and 2 barrels of beer. That would be on the line, and it would be on this line. That's also a candidate, and chances are that'll have more money because we made an extra barrel of beer. Okay, so there's two versions of this question. One is called the discrete case. This would be where there's a constraint that says all the barrels have to be complete barrels. You can't make a half a barrel or a third of a barrel, you can only make full barrels. And in this case, the question, this is a small enough question that we could actually, we wouldn't need something like Excel to solve it, because there's really only one, two, one of the choices could be make no beer, no ale. That should be intuitive, that's not the best answer. This is a possible answer, this is a possible answer, this is one. And that's it, there's really 1, 2, 3, 4, 5, 6, 7, 8 possible choices. And we could use something like Excel just to calculate what the problem is and take the best one. So in the discrete case, where we're only using integers, so integers are numbers like 1, 2, 3, 4, there's no halves or fractions. Integer barrels of beer. It's pretty straightforward to solve that one. But then there's the continuous case. Where we could have fractional barrel of beer. Of beer and ale. Now, if that's the case, then the possible answers we have to consider all the possible answers and then pick the best one. That's what this type of question is. And you could also do it to say, there could be a minimization problem. What's this, you could have a certain amount of money, and you want to buy some stuff, and you want to keep as much, what's the cheapest way to accomplish something? So these problems could be maximization problems or minimization problems. In the continuous case, then really any point in this whole region, any point in the shaded region, is a possible candidate as the best answer. And we'd have to really check all of them. And, for mathematics, there's technically infinitely many points in any region. So we'd have to check all infinite points and then pick the best one. But let's think about it just from a mathematical point of view. What are some answers we don't need to consider? So, for example, if we pick any of the interior points, let's say we were to pick a point right here, and we thought to ourselves, is it possible that could be the best answer? Is there an argument that you could use to say that there has to be a better answer somewhere? So this would be a point where I'm wasting some of the hops and some of the corn, but I'm thinking this might be the best answer. It's an interior point. So is there an argument you could say, I know for sure that's not the winner, that's not the best answer?
Isn't the best answer on at the crossing point?
Well, it may not, you're saying at this point here. That would be the max. All right, yeah, let's approach it from I was gonna kind of rule out some points and then leave some, but could we argue that this will definitely be the best answer? All right, so first could we argue that this point is better than this point? An external point is better than an internal point. So what's the argument there? Whatever we've made here as far as beer and ale, this point is further outside, so we've made more stuff and used more ingredients. So unless one of these became a negative number, like if you keep making beer, you're gonna lose more money. As long as they're positive, we would have more money by going to a more external point. Any point you pick here, you could just go this way or this way, and you'll have to do better, right? As long as you keep getting closer to the outside. Okay, so now we have this region that has two lines on it, any interior point would not be as good as a line going more up or more out this way. So that tells us that the best answer should now be somewhere along this border. So we really don't have to consider the interior point, we only should consider the ones along the border. Now, you suggested that the crisscross would definitely be the best one. Does anyone have an argument that it's probably true, but not definitely? If it was definitely true, then we could just say, let's find the crisscross and we solve the problem. Is there an argument it might not be true? It's a good candidate for the best answer, but not always true. Yeah.
I think it's more on the right curve, although on the right side, that goes towards the ale. Because ale is obviously more expensive. I mean, it sells for more money, so you can make a bigger profit. So I think maybe.
Right, it's a bigger profit, but it's eating up more resources.
Yeah.
And if these numbers were made more extreme, it might make more, if these numbers were larger, if they ate up more resources, it would start to make the idea of making more beer and less ale would make more sense. And if beer ate up a lot of resources, then answers going this way might make more sense. In other words, I could keep pumping these numbers up. I could pump these numbers up high enough that would make you say, all right, now this is starting to become a better answer, or going this way is starting to become a better answer. But the question is, would it always be this point? And the answer is no, because like I say, I could make the ingredients to make beer go so high. If I made this, 6 and 6, then most likely the answer would be just make as much ale as we can. Or if I made this, it could be ridiculous, I make this 100 and 100, then we should just be making ale, right? So if I change these two numbers to 100 and 100, our optimal answer will go down this line to this point. And if I made these ridiculously high, we would go up this way. And then this happens to be a question where, maybe using intuition, it turns out the best answer is the point in the middle. So now we have this extreme as a candidate, this extreme as a candidate, and also this one. Could it ever be possible that between this point and this point, along this line, could actually do better than the best of these 2 points? So, for example, we can see now there'll be examples where this would be the optimal answer, or this, or this. Those are possible. Is it possible to be somewhere on the line? So in the case where the ale uses up so many ingredients that we should just make beer, could it ever improve a little bit to make like a little ale and a little less beer? So let's say this was the maximum answer. If we started taking points along the line, could it ever, or even temporarily, make a better profit? Or would it always be the points on the corners? I shouldn't say corners, wherever lines intersect. If it ever made sense that just making beer is better than making ale, we would end up shooting up to the end of the line. There would never be a way along the way where ale helps and then ale starts hurting again, because these numbers are now fixed. So ale would never, it help us a little bit and then make a little more, it starts hurting. So really the only candidates that make sense are the ones on the intersecting lines. Now this happens to be a somewhat easy question because there's only 2 constraints, corn and hops, and we're making 2 things. So the constraints would be the lines in the middle. The dimensions of the picture are the stuff we're making. If we made a third thing, what else is there besides beer and ale? What do microbrewers make? Lagers? Let's say there was a lager. And let's say there was a third ingredient. How would we draw it? Well, we'd have a 3-dimensional picture. We'd have to have like a 3rd dimension, like 1 dimension coming at us. And then the hops, corn, and the third ingredient would end up being not lines, but they would end up being planes. Like a 2-dimensional surface. And then we'd end up making not a region, but we'd end up making a cube kind of thing. Now, the candidates there, it's the same concept, would be this cube that we would then make, the corners of the cubes would be the candidates for the best possible answer. Once we go into a fourth dimension, it's hard for us to, as humans, picture it, because we only picture 3 dimensions. But this could go up into 10 or 15 dimensions, and you'd make some kind of an object, and you'd have to check all the corners. So Excel has, and this is sometimes called a simplex method. Does that ever come up in any of your science classes? Simplex method? Okay. But it basically means you're given a bunch of constraints, and you try to either maximize or minimize something, and then you pump all this data in. The computer, or the Excel in this case, will calculate the 2-dimensional surface, the 3-dimensional cube, or whatever it is, and it'll check the corners for you and then pick out the best answer for you. So what would we have to feed into this, this type of question? What do we have to tell it from an Excel point of view? We're going to obviously have some box that will calculate how much money we're making. We want to tell it maximize or minimize this box. And then we want to say something along the line, subject to the constraint that how much ingredients we're using never goes above this number. And then hit a button and it'll calculate it for us. So how could we punch something like this into Excel? So here we have, pretty much, these would be just data fields. We're typing these numbers in. Here's our constraint. And what else would we have to need now? We want to be able to calculate how much money we make. So how much money do we make? We want to take how many barrels of each thing we make, multiply that. We would multiply how many barrels we make times the price we can sell them for, which will get this number. So let me just go over which fields are free and which fields are formulas. So this is a free field. We could type in any number we want, here, here, here. These are free fields. The constraints are also free fields. So there's no constraint on the price. Now, how many barrels? I'm going to let this be a free field too. The sales is going to be a formula. So the sales will be the price times the number of barrels we make. Same thing is true for L, same formula. Okay, so we're just multiplying the price times the number of barrels we make. And I could put as much as I want. I could say, well, if I sold 2 barrels right here, I've made $30 in beer, $20 in ale, for a total of $50. But I'm not following the constraint right now. I can say I made 50 barrels of beer, and I've made $770. I should make these, should format these to say currency. Okay. So right now I can aimlessly put any number I want for how much beer I'm making. But we don't want to do that. We want to meet these constraints. We never want to use more material than the 2 6s in this case. So how can we do that? And so this is the type of problem. It just takes a little thinking. Once you kind of get used to converting the question into what needs to be typed in, then these become pretty comfortable questions. But, so what we really need to do is that, what is our constraint? This is a free number. The constraint is saying we have 6 bushels of corn, 6 bushels of hops. How can we make sure, because I don't want to just randomly put a number like 50 in here, because I don't have enough material to make 50 barrels. I want to make sure that the number that goes in there never exceeds what? So we'll create right? So now it seems like it's a little interesting, we have to come up with something that's keeping track of how much stuff we're using. And then say that box must never be bigger than the constraint box. So what would go into a usage box? So for example, if I made 1 barrel of beer and 1 barrel of ale, then I used 1 corn plus 3 corns, which would be 4 corns. So I want to make this box be a calculation. So, and that should be pretty straightforward. And this one is a calculation box. So this box is saying, if beer takes 1 bushel of corn, and this is a free box, this is how many I've decided I've made, then 1 this box times this box means I've used 1 bushel of corn, plus 3 bushels of corn is used to make 1 barrel of ale. So I take 3 times 1, add those together, and that's where 4 is coming from. So this is I'm just setting up a box that calculates how much of the material I'm using, just keeping track of it. And the same thing is true for the usage of hops. If this is how much gets used per barrel, multiply that by the number of barrels, add that to this is how much is used per barrel of ale, multiply that by the number of barrels of ale we made, add the 2 together. And so it's just a box keeping track of how much stuff we use. Okay, so it's still now a pretty free-form spreadsheet. In other words, if I put in a 30 here, okay, what this is saying is, I've made 30 barrels of beer and 1 barrel of ale, and this is how much ingredients I've used. This box just keeps track of how much ingredients I use. Well, this is way too high. I've used 33 bushels of corn, but I've only had 6. So I went way out of bounds. But right now I can freely put any numbers I want in here. So this is my constraint, and this is the formula that's calculating how much stuff I've used up. When we want to solve this, we want to say something along the lines of, maximize this number, give me the best number here, but I'm going to give you some rules you have to follow. One of the rules is this box should never be higher than this box, right? And also, this box must never be higher than this box. If it follows those rules and can tell us what's the maximum number here, then we have our answer. So it turns out in this case, now this is obviously the continuous case, not the discrete case, because then any of the points along here could solve the problem. Okay, so we have to, once you kind of know, Solver's a little confusing to use. Sorry, I'll turn this off. Solver's a little confusing to use because it really gets into, you're putting numbers on your spreadsheet and you're asking for one of the boxes to be either minimized or maximized, subject to constraints. And now what you have to do is you have to set up your boxes to say this box must never be bigger than this box. So now we're going to kick off Solver. Probably, I forget how to use it in one. The first question is what box is being maximized or minimized. So you pick a box and then you check maximize or minimize. And then you can start pumping in. As you realize, there could be unlimited number of constraints. If we have more materials, we have 2 materials, so we'll have 2 constraints. But if we have 50 materials, you'd have to check in all 50 constraints. So we'll kick off Solver. And so Solver should now be on your tab up here. So we've set ourselves up that we have something we have a box, we have 2 boxes with our constraints and then 2 boxes that are calculating how much material we're using up. And those 2 combinations can be used to set up our constraints. So we decide we're going to take this box, the total sales box, as our objective, And we have a choice, we can maximize it, minimize it, oh, we could also, there's a third choice, we could pick a particular value. We could say, I want my profits to be $60, no higher or no lower. So in a profit thing, you would end up picking maximum, but you could pick a particular value too by saying value of. So we're just gonna say that box should be maximized. Oh, sorry. And we're gonna say that this box, G9, which is this one over here, we're gonna say that this box should be maximized. And now what we can do is add constraint after constraint after constraint if we want. The constraints that we're going to add, in this case, will be, you know, let me delete these, we'll just add them again. Okay. So I'm going to say that this box, the usage box, okay, I'm sorry, I'm gonna add a constraint, I'm gonna say this box, the usage box, I have choices. It can be less than or equal to, must be exactly equal to, greater than or equal to, required to be an integer if we wanna do a discrete case. So I'm gonna say is less than or equal to the constraint box. And I have to put the cursor in the constraint box and then click on the box. So what I'm saying here is, so I've already said we're going to maximize a particular box. Could have been minimized, could be exactly what we said. We want to maximize this box. And we're going to say that we're putting a rule that says this box must be less than or equal to this box. Can't go above it. Can't have this case where we have 6 versus 4 and I'm using 33. So that's what this constraint is saying. It's saying that C7, this box, is less than or equal to C6. So you can come up with any answer you want, but make sure that this box is less than or equal to this one. And then we'll put the same constraint in for the hops too. So I'll add this constraint, and it's, I can just do another one. This box must be less than or equal to this box, and I'll add that one. And then I'm okay. C7 is less than or equal to C6, D7 is less than or equal to D6. Those are my 2 constraints.
Wait, what was the equation that you put in the usage box again? I messed it up.
Okay, so the usage box. The usage box, this would,
Yeah, that's what mine did. Like the formula wasn't there anymore.
we said the usage box should be equal to how much corn per barrel of beer times the number of barrels of beer, plus how much corn per hops times the number of barrels of hops. You know what, I'm just gonna type it. Oh, this one's still here. Okay. So now we want to go to, and I'll just go through the steps again for solver. For solver, I'm gonna say, I want to have this box maximized, subject to this constraint and this constraint. And then I'll hit solve. Okay, so what this is now saying is it found an answer for us. Have you guys punched in the same number after, did you get 52.5? Okay, so what this is now saying, once the formula has been completely punched in, we actually end up using all our ingredients. It wasn't definitely going to happen that way, but we should have definitely used up one of the two ingredients and possibly both. And then what it's saying is, we can make $52.50 by using a certain strategy.
Yeah, I think
Or, well, one of the numbers different, or? You have one, 2, 3, 2, $15 and $20. And you have sixes here? Did you calculate 2 sixes? Which one? Okay.
What cells do you want to change?
Yeah.
We,
Just changing value of
No, like when you go to solver, actually make it the maximum, it has to change
cells. This is by
variables.
changing variable cells, which cells you are allowed to change.
If 4 or 5.
when you were inputting the solver?
Yeah.
Right above the
Parameters
constraints.
for solver.
Okay. So let's see,
So you have
Above
F4 and
constraints,
F5.
F4 and F5.
okay. Oh, okay, sorry about that. So, yeah, by changing barrels. That's a good point, sorry about that. The fields that are allowed to change are how many barrels we can make. So it'll be that range. So that would be, in this case, assuming you use the same squares, it would be F4 to F5. So by allowing those to go up and down, we're trying to seek the best answer. So what answer I'm curious now, were you saying nothing could change?
No, I put, put like C7.
Okay. Okay, I thought if no cells could change, then it still found an answer, but I thought that would be strange. Okay.